So today we're going to finish up talking about geology and groundwater and talk about some regions of groundwater in Montana. All right, so if we move around the state of Montana, what kind of hydrogeology do we expect? And that's going to be dependent upon the geology of the state. So as a brief reminder, we had started talking about geology and groundwater and about how the geologic history controls what kind of groundwater systems we might expect, right? And we had started talking about sedimentary aquifers, how the hydraulic conductivity and the porosity and the storativity was really controlled by sort of the grain size and distribution, which is the depositional environment. All right, so all that stuff that you're learning in Mark's class about sedimentology and depositional environment, that's critical for understanding what the subsurface structure looks like and how that controls the hydrogeology. In particular, for us in hydrogeology is really thinking about what's the degree of the fine sediments, because they basically tell us whether there's going to be permeability or conductivity or not. So when you've got a lot of clays and silts, you're not going to have a good aquifer. But if you've got sands and gravels, you're going to have a good aquifer. And so a big thing for us is thinking about what is the percentage of fines, essentially? And then how are they distributed in space? All right, we also said that groundwater generally follows the bedding plane. All right, and so if we think of the world as a sedimentologist, you know, the principle of original horizontality, right? I think that's one of our first Geo 101 principles. Everything is these flat beds, right? And that's basically true for sedimentary systems. And in general, the groundwater will follow the bedding plane, all right? And we've done these calculations before. We figured out the average hydraulic conductivity of a sequence of layers, either horizontal in the direction of the layering or vertical against the direction of layering. And it turned out that the hydraulic conductivity across the bedding was set by the lowest hydraulic conductivity layer, essentially. And the average hydraulic conductivity parallel to the bedding was given by the highest, or more affected by the highest hydraulic conductivity. And so what that means is, in general, if we have flat lying beds, we get really long, flat groundwater systems. And so we'll talk about this later, but in general, we often make the assumption that groundwater flow is dominantly horizontal, all right, and not vertical. And it follows these bedding planes. This can get affected by the degree of folding, all right? So if our beds are really folded, in general, we're still going to follow the bedding plane, our flow paths. And so we'll get flow paths that sort of can be vertical where the bedding is vertical. And that happens both for synclines, all right, and for anticlines. Okay, and then finally we talked about faults, and faults are tricky. They cause a discontinuity in our bedding, first of all. And sometimes, depending on the fault mechanics, they can be high hydraulic conductivity or low hydraulic conductivity. And the thing that controls that, just like anything, is the degree of fines in the fault. So fault gouge is like where you break up and grind the rocks, and you can grind them into really fine clays. Right? So if you have a lot of fault gouge, you fill your fault with fines, you have a low hydraulic conductivity fault. If you don't have gouge, if you just break the rock, you've got a big fracture. We'll talk about fractures here in a second. Then you'll have a high hydraulic conductivity. So really, it's the degree of gouge that controls this. How much fines, how much broken up and ground up bits of rock are in the fault. And these faults, a single fault can be both high K and low K. The gouge is really heterogeneous, it turns out, in these faults, in most faults. And so, for example, the San Andreas has areas where there's zero gouge. It's just a huge open fracture. And there's areas where it's all just full of clay and really, ground up gouge. So the faults can be both. And the same fault can be a barrier to flow in some locations and permeable in others. Okay, so understanding the structure, the first thing I do when I think about a groundwater system is I think, well, what's the local structure, right? And that starts to tell me what kind of flow system might I be dealing with. All right, and we said at the very beginning of this, there's sort of two principal kinds of aquifers that we consider. One is the porous media aquifer, and the second is the fractured aquifer. And that's what we're going to start talking about now. And we'll get to this here in a little bit, but in Western Montana especially, we have both types, but the fractured aquifer is an important type for us to think about. All right, so let's, oh, that's not what I wanted to do. Okay. So who here has taken structural geology? Two people. All right. So we'll do, first of all, we'll do a little bit of basic structure. So we did that a little bit already with anticlines and synclines. But now with fracturing, and I feel like a lot of structure is figuring out what the orientation of stress is and how that's changed the shape of the beds and the bedding. And another thing that the orientation of stress within the crust does is control the fracture orientation. So if we have a rock, a block of rock, within the Earth's crust somewhere, the plates are always jostling around. And as they do that, they exert stress in the rock. And stress is essentially the forces inside the rock pushing it in different directions. That's a very non-technical description of stress, but it works for what we're doing. All right. And what we generally do is we try to break the stress up into its main components. So stress is a vector. It's actually a tensor. And it has a direction and a magnitude, and we break the stress up into its principal directions. And so the symbol for stress is sigma. And the direction of the highest stress. So let's say we're in a setting here where the plates are causing compression, all right? Then the direction of highest stress would be the direction, sort of this compressive direction, and we call that sigma 1. So sigma 1 here is our highest stress. And then we might have, we break it out, this is sigma 2. This is our intermediate stress. And then we have sigma 3, and this is our least. Oh, that's just a 6. So there's these principal, my main takeaway here is that at any point in space in a rock, we can figure out what's called the stress orientation, right? And that tells us where the biggest compressive and extensive stresses are. And as a result of the orientation of stress, all right, and the differential stress. So because sigma 1 does not equal sigma 2, does not equal sigma 3, the rock's under what we call differential stress. And it will create fractures if we exceed the rock's strength, then we create fractures. And depending on the stress state, those fractures will be oriented in a certain direction that depends upon the stress state and the orientation of sigma 1, sigma 2, and sigma 3. So as an example, in this case, we might end up with a series of fractures that all trend in a similar direction. So the fracture orientation is dependent upon the stress field, all right, and the differential stress. So, or the orientation of differential stress. And when you take a structure class or a geomechanics class, which we don't offer here, but are offered in some other universities, you spend a lot of time thinking about how the stress state controls the orientation of fractures. I'm not gonna expect you guys to do any of that in this class. All I want you to know is that differential stress causes fractures, and those fractures actually tend to be oriented in a certain direction. All right. And that is complicated. It depends, over geologic history over a long time. As the plates jostle around, the state of stress changes within rocks, and we'll get fracturing in a bunch of different directions. But in general, a fracture network will have a preferred orientation or sets of orientations. So let's so oftentimes they'll be sort of sub-parallel. All right, so here, if I took one block and I subjected it to a single stress field and the rock was fairly homogeneous, I would actually end up with pretty uniform sub-parallel fractures along a given orientation. And so in hydrogeology, oftentimes, well, let's say this. The principal issue with fractures is that the fracture has very high hydraulic conductivity, and the matrix, the adjacent rock, can be very low conductivity. The fracture will always be much higher than the matrix. And so as hydrogeologists, one of the biggest questions in hydrogeology is these fractures, we don't know. In the real world, we don't know exactly how they're oriented. We don't know how long they are. They're kind of random features. They have a preferred orientation, but we don't know sort of their length of propagation. They're really complicated. And so we're always trying to think of ways to simplify the real world. And one of the principal ways we do that is say, well, let's assume that we have sort of parallel fracture sets, because there's easy things we can do to calculate things like fracture porosity. So often we might assume a parallel fracture set, or we go out in the field and map preferred orientation. So we'll go measure the strike and dip of the fractures we can see in rock outcrop or within boreholes. And we map those and we try and get a preferred orientation and spacing of the fractures. So they often have a preferred orientation and a spacing or distance between fractures. So let's just zoom in on a fracture network. So if we assume parallel fractures, and I'm going to zoom in on a fracture network. This is kind of a hard drawing, so we'll see how well I do on it. I've got a block of matrix. And then adjacent to it, I've got another block of matrix. And then I would have another block here of matrix. All right, so these are my matrix blocks, and they are separated here. So this is my fracture. So I've got two parallel fractures here. They are separated by a distance B. So this is my fracture spacing. And this B goes to the midline of each of these fractures. And each of these fractures has a known, well, maybe it's not known, but has an aperture. So this distance here is B. And B is the fracture, or little b is the fracture aperture. That's just the width of the fracture. So I'm just, and let's say that they have a height. My matrix blocks have a height here of H. And they've got a length in and out of the board here. This length here is L. So I'm going to think about a block here that I'm going to consider a cube of our fracture media that goes from midline to midline of the fractures, all right? And I'm going to calculate the porosity. So I need to calculate A, the volume of the voids. So what can you guys think of what the volume of 1/2 of this fracture? So this, let's say this side over here, right? It's gonna kind of be a cube that runs back like this. What's the volume of that cube or rectangle? Well, what's the equation for volume of a rectangle? Surely you guys know that one. Okay. Okay. Now we're getting somewhere. So B over 2 times what? Times L, right? And I've got in this cube here, I've got 2 of those. Right? I got this one on this side and I got this one on this side. So my volume of voids, or my volume of fractures, is 2 times B over 2 times H times L. And that equals B times H times L. That 2 and that 2 cancel, little b H L. All right, now I got to calculate the volume total of this cube. So that's the total volume from B. So what's the total volume here? Big B H L. All right, and remember my porosity equation is here. I'm going to call this the fracture porosity. It's the volume of fracture divided by the volume total. So that is little b over H over L divided by big B over H over L. Those H's and L's cancel out and I get little b over big B. So the fracture porosity is the ratio of the aperture to the fracture spacing. This is for parallel uniform fractures. All right. So parallel as we consider more and more complicated geometries of fracture networks, we can make this equation more complicated. But in general, the rough fracture porosity can still be estimated by the aperture divided by the fracture spacing. Finch. Good question. Well, we're taking the volume of this total cube here that goes from half of B over to half of B, and the width of that is big B. The fracture spacing goes from midline of this fracture to midline of this fracture. So it's big B is this width, the height is H, and the length is L. Does that make sense? So fantastic question. And the short answer is we're still trying. GPR. So herein lies the rub and why it's really hard to do. A big fracture would be like the width of your hair. And a fracture, we'll look at the permeability of fractures a little later in the class. But they basically go as the aperture cubed. And So a very small fracture has a very high hydraulic conductivity. And so even radar has something resolving like as hairline as a fracture. They could see big fractures, centimeters they can see, but 0.1 to 0.01 millimeters, you're just never going to see it with a radar. Some proposals I've been on in the past trying to look at these have been looking at just changes in the seismic velocity. So you're not trying to reflect, you're not trying to get a reflection in the seismic waves. You're just looking at how fast they propagate through the media. And in particular, shear waves are very affected by fluid-filled fractures. So there's some idea that shear wave tomography could give you some idea of the fracture density, but we don't have great ways to find the fractures. The ways we do it right now are to drill boreholes or to look at rock outcrop and map the statistics. And then if we want to think about how a groundwater system in fractures behaves, we can only do it probabilistically. We can just say, here's the statistics of the fracture networks. We could make a bunch of different fracture networks that honor those statistics. But yeah, it's really hard to see them in real life. And I don't know if and when we'll ever. Other ways that I've been involved that we have done it, are doing it right now, is injecting a fluid into the fractures and then looking at how that changes the electrical resistance. So you can inject, for example, if you injected salt water into the fractures and you measure the electrical resistance between two electrodes, you could potentially see that fracture as a really big, highly conductive zone. So that's another way people have done it. None of them work really well. This is the bottom line. It's really hard. It's probably the principal, well, it's one of the big problems in hydrogeology is how to deal with fracture networks. There are some things we can do though. So we don't have to just bury our head in the sand and say, hey, we don't know where the fractures are going. We can do things like understand that they're often preferentially oriented. So we can, and they often have pretty, not uniform, but reasonably uniform spacing. All right. And so we can get things like spacing, we can get things like direction. And you can actually, you can end up characterizing these things with some degree of confidence. So let's think about how these, if we, fracture networks. And how do fracture networks control hydrogeologic systems? So the fracture network systems that I work in a lot are mountains, all right? And we'll talk about this here in the later part of the class, but almost all the mountains around us in Missoula are actually made of sedimentary rock, all right? And they have bedding. So as an example is if this is Mount Sentinel, here's the M here, here's campus. The general bedding looks something like this. There's the Bonner sandstone. And then the Mount Shields siltstones, and then the shepherd limestone. All right, and these are all parts of the belt sequence. All right. So this mountain is made of sedimentary rocks, and in general, we would expect sort of fluid flow to be parallel to bedding. But it's a 1.5 billion year old sedimentary rock. It's been part of, you know, at least 2 mountain building episodes now. And so it's fractured. It's got a lot of fractures in it. And those fractures are not necessarily oriented parallel to bedding. So in the belt, for instance, we might have a fracture network that looks something like this. All right. And the general orientation of the fractures does not have to be parallel to bedding, and in many cases is not. So in this case, groundwater flow will follow preferred fracture orientation. Right, and so in general, the groundwater moves sort of along these fracture networks. So some key things that control the groundwater flow are the fracture orientation, the connectivity, so you can imagine one of the really hard things about fracture flow is that the water is moving in discrete fractures. It's not moving in this big porous media. It's a very discrete phenomena. So if I had, for example, if I had a well and I drilled it right here and I did not intersect a fracture, I'd just be in the matrix and I wouldn't see much fluid flow. All right. If I had a well and I drilled it deeper and I happen to intersect this fracture, then I'm going to get fluid flow. So fracture networks are really hard to work in. They're very discrete, and wells that are right next to each other might be finished in a fracture or might not be. And they could have completely different behaviors, depending on whether they're in the fracture or not. So one of the real key takeaways is that the groundwater flow is very discrete. It's a very discrete flow path. And those flow paths are controlled by the fracture network characteristics, orientation and connectivity. An example of that is if I just have a fracture out here that just sort of stops, there's nowhere for the water to go. It'll just fill up with water, but it won't transmit water. So you not only do you have to have fractures, they got to be connected to the surface and to each other in order for water to be moved along it. And in general, because the hydraulic conductivity of fractures are so high, the fracture orientation will trump the bedding. So in general, fracture orientation is more important than the bedding. Okay, so the dominant things to take home with fracture networks is the fractures are it's really hard to know where they are. The groundwater flow is very discrete within them. And the thing that controls the groundwater flow is the orientation, direction, and connectivity of the fractures. All right, so let's take a 5-minute break, and then we'll talk about Western Montana and use it as an example to talk about the different kinds of aquifers and how geology controls the type of groundwater systems that we see. At the groundwater regions of Montana. So this is a map of from the groundwater atlas. And published by the USGS. And these are broad divisions of America, and they're put into these provinces or of different groundwater resource type. And Montana falls into 2 different provinces. It falls into the Rocky Mountain Division, which is this orange stuff, which is the Western Montana section that we talked about, this sort of basin and range mountain dominated system. And then the eastern half falls into the Great Plains province, these gently sloping sedimentary basins. So we can zoom in or define this a little more, and we can look at the kinds of aquifer systems or the major aquifer systems that are in Montana. In Western Montana, we're in the Northern Rocky Mountain Intermontane basins. So these are these basin and range systems. We're going to look at them in detail here in a second. In Eastern Montana, we're in the Northern Great Plains Aquifer system. And we'll look at both styles of aquifers in these 2 systems, but those 2 are basically what drive us here and our conceptual models in Western Montana. So the first thing that I want to highlight is that here, all the quaternary alluvium is mapped in yellow. And quaternary alluvium is the sediments deposited by active river systems, right? And the first and most fundamental thing you should take away from this class is that every river system has an alluvial groundwater system associated with it, and they are completely tied together. So you can't have a river without an alluvial groundwater system. It will dry up. You can't have one or without the other. And every river, when you roll up on a river, know that there is a groundwater system of some varying size around that river system, and that the groundwater and the river are talking to each other all the time. Another key takeaway, we're going to focus in on Western Montana here. You can see these big basins in between the mountains that are mapped out. So here's Missoula, here's the Bitterroot Valley, 9 Mile Valley, here's the Flathead Valley, here's the Swan Valley, it's Lower Flathead, Upper Flathead, Clark Fork Valley. So you can see these bigger valley systems mapped out in Western Montana. These are this now is a map of the aquifers, the alluvial aquifers. And all I want to point out here is that in every alluvial deposit is an alluvial aquifer, right? And they follow the big rivers. So here's the Bitterroot River alluvial aquifer system, the Clark Fork River alluvial aquifer system, the Flathead, Swan, and Flathead River alluvial aquifer systems. You can see the Yellowstone here and the Missouri up here. So you can see every river has this alluvial aquifer with it, and they basically follow the natural river network. So now we're gonna focus in on a Western Montana valley, all right, system, and this is for the Deer Lodge. This was this particular cross section was developed from a hydrogeologic study in Deer Lodge, but this setup is exactly what we have in the Missoula Valley. It's exactly what we have all over Western Montana. And here's the basic idea. We have a mountain block, all right? This could easily be, for example, the South Hills in Missoula. We got a mountain block here in gray. That mountain block has some mountain aquifer system associated with it. A lot is unknown about these mountain aquifer systems, but it has some mountain aquifer system. It's bounded by a fault. And again, remember these faults, they can be either impediments to flow or conduits to flow. We're not sure always. We have to drill and find out if we want to know. Okay, the lowest sediments in our valleys, or the deepest sediments out in the valleys, the oldest ones are Eocene and Miocene, or in the olden days, Tertiary. And back then, Montana was a much drier place. And these sediments are really full of silt and clay. All right, so remember, as hydrogeologists, we're just interested in how much silt and clay there are, because that tells us whether or not there's good aquifers. So these tertiary systems, silt and clay, they're not good aquifers. The whole South Hills in Missoula is these tertiary sediments. The whole north side where the dump is these same kinds of tertiary sediments, really clay-rich silts. All right, then we move out into the quaternary deposits. And these are where our big aquifers are. So the Missoula aquifer is in the quaternary, unconsolidated alluvium. And they're directly tied to the river system. So these are shallow. They're usually less than 100 feet, maximum up to 300 feet. And they're in direct communication to the local river system. So the Missoula Aquifer, maximum depth is 100 feet. Beneath it are these tertiary sediments that don't produce a lot of water. They go down to some unknown depth. We think about 1,000 feet in the middle of the Missoula Valley, but we don't know. And at least 1,000 feet. And the Missoula Aquifer is directly tied to the Clark Fork. Depending on where you are and what the mountain block is made out of, there is structure, there is folding of the deposits and faulting within the mountain block, and that may exert some control on the groundwater circulation within the mountain block. So my main point here is that these mountains are often sedimentary, they have fracture networks, there are mountain aquifer systems. There's very little known about them. All right, and so, you know, this is a big area of my research, is trying to understand these mountain aquifer systems better. But they do have flow, and they do have aquifers. They're just really complicated and hard to work in. Here's another cross section again of Western Montana. This just shows you sort of the depth and what these valleys look like. So we have bedrock bounding the valley aquifers, and then these valley aquifers are really where we get in Western Montana. 99.9% of our water resources come out of these valley aquifers. All right. So all the water we drink here in Missoula comes out of our valley aquifer. All right. It's these unconsolidated alluviums, and they're directly tied to the surface water. So another really important thing that happens all over Western Montana and is a big focus of the state's groundwater research right now is when we start extracting groundwater, we are extracting surface water. This is the same system. They're directly tied together. So they're very tightly coupled systems. You can't pull groundwater out of the Missoula Aquifer without actually changing the flow of the Clark Fork. Yeah, it's a good question. We pull these, this aquifer, the Missoula Aquifer is extremely productive. We pump like 1,000, I think 1,000 gallons a minute. Some of these wells are easy 1,000 gallons a minute. That's still not a lot of water compared to the flow of the Clark Fork. But we do reduce the flow of the Clark Fork. This is water that would, we'll talk about the Missoula Valley aquifer system in more detail, but essentially what happens is the water leaves the Clark Fork here at near the Hellgate, and then it returns back near the junction of the Bitterroot and the Missoula on the west end of the valley. And we're taking discharge that would have entered the river and using it, essentially. Some of that is consumptive use, so some of it is water that won't go back into the system, but anything that we use that goes back into the sewer system gets discharged back into the river. So not all of it is consumptive use, and that's an important thing. The only consumptive use is irrigation. So when you irrigate your lawn or your garden, those plants use the water and they send it back into the atmosphere. But actually using the toilet, that's not a consumptive use of water. It sends it back into the river. I think one thing that I want to highlight here is this a big area of research right now is this arrow right here. And that is how much water is entering these alluvial aquifer systems from the mountain aquifer systems. If there's a lot coming in here, that means that we can pump more groundwater out of this alluvial system, and we're depleting, say, some of the mountain aquifer system, but we're not necessarily depleting our surface water body as much. This just shows the idea here that, you know, this is the same resource. So when we install a well within our alluvial aquifer system, we'll lower the water table as we pump the well, and we'll draw water out of the river and into our well. So every time we install a well in Western Montana, we're actually pumping river water. And it's a kind of a, I'll just say there's a lot of hand wringing going on trying to determine how we regulate groundwater extraction in Western Montana, because all the surface water rights have been given out. You can't get a surface water right anymore. The only way, if you're a business and you want to develop a new business and you need water, the only place you can get water is groundwater. But guess what? That's surface water. So there's some more legal wrangling to be done in this state on this, especially in Western Montana. Okay, let's move out east into the Northern Plains aquifer systems. And these are maps of the different aquifers in eastern Montana. And what I want you to see here is first the difference in scale. So in Western Montana, let's say the Bitterroot aquifer system was a small little yellow blob that occupied, you know, a little bit of Ravalli County down here. This is the lower tertiary aquifer. This one system right here is the lower tertiary aquifer in eastern Montana. This is a huge aquifer. It's very large. All right, so the scale is very different. These are very big sedimentary sequences, and they have large aquifers within them. Here's the basic idea. You know, here's the front, the Rocky Mountain front, and then you've got these sedimentary systems that move out into eastern Montana. So this is the east, this is the west. And in general, these aquifers are recharged at the mountain front. So the source of water to these systems is at the mountain front, and then water flows away from the mountain front from west to the east through these aquifer systems. And these are large regional groundwater systems. They are flowing from the Rocky Mountain front. Some of them are going all the way out to the Mississippi. They're huge aquifer systems. The water in here could be millions of years old. In fact, a lot of it in the middle of the basin here, it was deposited in the Cretaceous period in an interior seaway. So it's like, you know, 60 million years old, and there's still seawater left in there. So it's still really salty. Fresh water hasn't flushed all the seawater out. So in the middle of these basins down deep, that water's still really salty with this leftover seawater. So in general, there's huge aquifers out in the eastern Montana and the Dakotas. The trick is finding places where it's not still salty. So nearer to the mountain front, it's closer to the area of recharge. It's had more time to flush or more flushing, and there's fresher water. But as we move out east into Western Montana, we're going to get into saltier and saltier water. So for many of these small towns in eastern Montana, they're just really, they're actually, it's really dry out there. It's very hard to find surface water. And they're, they have a heck of a time trying to find fresh, good groundwater. Even though they're sitting on these huge aquifers, a lot of them are still salty. Um, this map shows vertical slices of these aquifers, starting at in the tertiary and moving down into the lower Paleozoic. So at various depths here. And I guess what I want you to see is the extent of these aquifers. So for example, this tertiary aquifer covers parts of North Dakota, Montana, and Wyoming. Like it's a big aquifer system. But as we go deeper, they get bigger and bigger and bigger. So the lower Paleozoic system goes from the front, the Rocky Mountain front, covers all of eastern Montana, northeastern Wyoming, and most of the Dakotas. This is a huge aquifer system. As you go deeper, they get bigger. So the deeper you go, the bigger the aquifer system, the longer the flow paths. Problem is they're really salty down there. So this is a cross-section view of the Powder River Basin. Starts off here at the Rocky Mountain front, and you just see that this is west, this is east, and the groundwater is basically flowing through these sedimentary systems out to, you know, North Dakota. This is the Minnesota boundary. So these aquifer systems are flowing all the way to the Mississippi. All right, they're huge, big regional flow systems. Down here in the deep parts of them, they're so salty that you don't want to use them. And this is where they're producing a lot of oil and gas, is down here in these salty saline aquifer systems. For most of eastern Montana, the groundwater that we use is either this green, this is the Mississippi limestone, the Madison limestone, or in the tertiary systems like the Fort Worth sandstone. So these are the main places they get water in eastern Montana, are these upper two layers. And down here beneath this Cretaceous shale, nobody's really producing water. They're producing oil and gas down in here. Yeah, this is a potentiometric map. It shows the head contours of aquifers in the northern Great Plains. And basically, it's just showing that here at the mountain front, in general, we have higher groundwater heads, and that these heads move across North Dakota towards Minnesota is the general flow direction. So where these flow paths exit, it's in areas of North Dakota near the Minnesota border. And there's these big saline lakes, and the water moves up and just basically supplies these salty lakes that sit out there. Some of them make it into the Mississippi, but you know, basically there's a recharge point, the mountain front, and there's a discharge point. in North Dakota. And you have these big, long regional flow systems. I usually include this because there's an analogous aquifer system that's very famous. So we're up here in Montana in the northern Great Plains aquifer system, but just south, on the south side of Wyoming, they have delineated it as another aquifer system. It's the same type. It's these big regional groundwater flow systems that are recharged along the southern Rocky Mountain front here in Wyoming, Colorado, and New Mexico, and flow through these same age aquifers. So this is the tertiary system. But one of these aquifer systems, the High Plains aquifer systems, is called the Ogallala. And it's like a really famous aquifer system because all the farmers out here in Kansas and Oklahoma and Texas are essentially mining this water to grow our bread, all right? And what they're doing is they're using water that was recharged mostly during the last ice age, when there was a lot more precipitation falling in these mountain fronts, and supplying these aquifer systems. So much of the water that they use is, 12,000 years old at least, some of it even older than that. So this is the Ogallala aquifer system. When you hear about it, it's the exact same kind of aquifer system that we have in eastern Montana. It's just really famous because they're mining the water and they're running out of it. All right, so one of your assignments, or one of your questions for your homework assignment, is to start developing a conceptual model of groundwater flow for Lolo Creek. So as our final project, you guys are gonna develop a sort of simple groundwater model that calculates how much water pumping a well would extract out of the Lolo Creek, right? So we're gonna tackle two things as part of this final project. And the first step here is developing a conceptual model. And I'll just show you that, or tell you that many of these, as an example, this is a simplified conceptual model. It takes the sort of general geologic structure, right? Mountain block, faults, sedimentary valley with a river in it, all right? Alluvial sediments on top of tertiary sediments on top of bedrock. Alluvial groundwater system interacting with the surface water system, all right? So one of the things that you're gonna do is create one of these for Lolo Creek. And in order to do it, I want you to know the general geologic history of Lolo Creek area, like what's happened there, and the basic geology of it. So, hint, it's going to be something kind of like this. There's going to be mountain blocks. There's going to be an alluvial aquifer system in the middle of it. I want to know sort of what the mountain blocks are made out of, and what sedimentary sequences might be in the sedimentary valley in the center. We want to know things about like general sources of recharge and discharge to these systems. So here it's kind of this conceptual groundwater table, shows areas or ways that water enters the groundwater systems and exits them. Oh, the other thing that's in here is that should be in a conceptual model is what are the major aquifers and aquifer types in the area, right? So this sort of shows these quaternary alluvium unconsolidated deposit aquifers and adjacent mountain block aquifer systems. Now, for the final project, well, let's put it this way. This portion of your homework is me getting you to start working on the final project now. So don't write this on a piece of scratch paper and draw a shitty cartoon. All right? Think about this as your first section. This will be probably your first and maybe second section of your final project. I want you to come up with a drawing, all right? Preferably using some computer illustration program. So Adobe Illustrator is one that you can pay for. I use a program called Inkscape. It's a free drawing program. I want you to come up with a conceptual model, figure, all right? And then you're going to write the text that explains the figure, all right? And one section of that will be geologic history. I do not want 3 pages of in-depth geologic history of Lolo Creek. I need to know what's important and pertinent for me to understand your hydrogeologic conceptual model. So as an example, you know, what's really important for us is that we have mountain blocks of some kind of rock. So it's important for us to understand what kind of rock was deposited, how the mountain blocks were formed, what kind of faults we might expect. And then recent geologic history is really important because we need to know something about these unconsolidated deposits. So tertiary through quaternary, you know, what is controlling the depositional environment for these sediments. Then you need to have what I call hydrogeologic framework. So what are the principal aquifers and their type, and what kind of, you know, interactions, or I'll say what are their relative sizes and their interactions with surface water bodies. So hydrogeologic framework is essentially going to be principal aquifers and types that you think might be there and their general behavior. And then the final thing that comes as part of this conceptual model are things like we want to know sources of recharge and discharge, interactions with surface water bodies. You know, what are we'll learn more about these, but they're called boundary conditions that control how much water we have and what's available for us in our groundwater system. All right, questions on the conceptual model. I tried to spell it out on the homework assignment, but I'll just say that, you know, we talked about this with Enyumark, but developing a conceptual model, developing our idea of how the groundwater system works is really important. And we have to use our background knowledge of groundwater, of geology, and basic understanding of what controls groundwater flow to come up with these conceptual models. Yeah, Finch. You should type it and print it and turn it in. The reason why you should type it is because then you've already got 2 sections of your final project sort of knocked out, or at least roughed out, right? So do it on the computer. Every year I do this, and every year somebody turns in a hand scribbled paragraph and a cartoon. And I just think, why did you just wasted your own time? I'm trying to get you guys to get a head start on your final project. I'm doing it for your benefit. So print it, write it out, and save it, and you'll all of a sudden you're already on your getting started on your final project. Okay, we don't have class Thursday. It's a break day. It's one of these spring break days. So Tuesday we'll have to hit it hard, and fell behind a little bit today. So, but we've only got 7 minutes, and the stuff I'm about to get into gets really. We won't really. I'm just going to confuse you with 7 minutes. All right. Any questions, comments? Cool. Well, have a good rest of your week. And we will see you next Tuesday.